Okay, so last day our discussion was about flow measurement. We studied the basics of flow measurement, and then we discussed about these points, laminar versus turbulent flow, and we discussed about Bernoulli's equation, and that Bernoulli's equation is basically a statement of law of conservation of energy. That means energy is converted from one form to other. So if you have reduction in the static pressure, there is an increase in either of the other components, that is the kinetic energy or the potential energy. So that we explain the flow across constrictions. Okay, so there is the arrow across along a constriction. When the fluid flows, there is increase in velocity. That means the kinetic energy increases. Consequently, there is a decrease in the pressure, the static pressure. Okay, height is same, so h1 equals h2. So there is a transformation from static energy to kinetic energy. That is what. Based on that, we were discussing about flow meters. Say flow meters, two parts. We will say you will have a primary element and a secondary element. Primary element interacts with the fluid, and the secondary element converts this interaction into some reading. Okay, it indicates a reading. And we saw that there are broadly two types of flow meters, that is positive displacement and rate meters. And positive displacement, there will be some component within this, usually a mechanical component, which is rotating within a chamber, and this rotation will be caused by the fluid. A simplest example of positive displacement type of meters is your domestic water meter. Domestic water meter, where you have a disc, usually a disc which is rotating. So there is a nutating disc, that is what you call. Usually the domestic water meters are nutating disc types. Then we started with this inferential or rate type of meters, and we discussed about orifice plates. Orifice plate is a simplest one, which is widely used in industry. It is accuracy is less, but it gives you an estimate of what is the fluid flow. Basically, it has it's just a plate with a specific shape hole within it, and through which the fluid flows. And you apply the Bernoulli's equation, and you will be able to relate the area, cross-sectional areas, to the flow, or that is, as we discussed in this expression, you will be able to relate the cross-sectional areas A0 and A1 to the flow, and this is the series, the coefficient of discharge, to the flow. Or you would be able to relate the the flow to the diameter, flow to the differential pressure delta P. So, and K is a constant, so that depends on the coefficient of discharge of this particular type of plate. So we have discussed this thing. You can see the lecture for that, the recording for picking up from there. Then you saw the advantages. It's inaccurate. 5% inaccuracy might be even be there. So you cannot use it for turbulent flows, laminar flows. There is a pressure decrease there, 50% even loss of pressure will be there downstream. Putting this plate there, it will reduce the pressure. So today we discuss about Venturi tubes. So this is the Venturi meter, whatever you call it is. Venturi is again Italian, and this Venturi meter is basically an application of Bernoulli's principle again. You see that this has two sections, section 1 and section 2, and there is a converging part and a diverging part, for this Venturi meter. And it's a 19th century guy who still we will apply the expressions are more or less the same as the orifice plate. Basically, you apply the Bernoulli's equation at the two sections, section 1 and section 2, That means at the constriction and at the initial part, and you balance them. Z1 equals Z2, horizontal, the pipe is horizontal, so you will just have an expression in terms of the head and difference of the pressure heads at two sections. So rearranging these terms and expressing in terms of the continuity equation. Continuity equation basically states a mass, volumetric mass flow is constant, that is a cross-sectional area into velocity will be constant. So you get an expression for V1, you make a substitution, and finally we end up with this expression. But this is a theoretical discharge, but the actual discharge will be much lesser. That is what it is, having a parameter called as a CD, coefficient of discharge. So that is a parameter that governs there. So broadly you can say that you have a relation like Q is equal to K into root of P1 minus P2. That is the relation. Square relation exists, just like the case of a orifice plate. A square law relation exists between the flow and the difference in the pressure at these 2 points. So in industrial meters, usually we make this principle of differential pressures. You record the pressure before the construction and at the construction, and that is where the pressure becomes minimum. Vena contracta, that is the pressure, isn't it? So pressure becomes minimum there, and you will have this parameter K for the particular type of Venturi meter, and you can make a measurement. So these are the applications. So you could use it for turbulent flows as well. Okay, where liquids which are having suspended particles, they can also be used. You can use them in such situations also. So and can be easily installed. All those things are there, and the pressure loss is much lesser than that of orifice plate. Much lesser drop in pressure occurs in Venturi meters, say 10% loss of pressure downstream than the upstream case. So in the orifice place, around 40% loss in the pressure head happens. So this is a particular Venturi meter which is installed in a pipeline in an industry. Say you see the typical thing, and there is a tapping there, vent hole. This is a vent hole. These are vent holes. So you are recording the pressure at these 2 points. And you are transmitting it. That's what. So you have something called as the low pressure connection, that is P2, and this is a high pressure connection, P1. And then there are vent ports and drain ports. That is vent ports for gases which could be trapped at the top, and drain ports for suspended particles which could be trapped at the bottom. So these are there. This is a vent port and drain port. Drain port is there, and this is a vent port. So, and this is a hobby example. Okay, this is if you go to this link, you could make a you'll get the instructions to make a Venturi flow meter using Arduino. Do give a try if you have time. Do give a try. Okay, so that's regarding Venturi meter. The next we discuss is a Pitot tube. So Pitot tubes, they are one of the widely used flow meters to measure the velocity, air velocity. So say you will find them on aircrafts, on F-16 means Formula 1 cars, okay, F1 cars. So this is your Pitot tube on an F1. So they are studying this parameters of this vehicle. So the Pitot tubes will be found at different places, in fact, on an F1 car. This is on the front part of the car. Okay, so and basically it is an application of Bernoulli's principle, and we'll see how it is utilized. So if you have this relation, say you have this relation, the construction is here, and this is the area corresponding to the construction, and the velocity and the pressure at these points, So the total pressure, you can say total pressure PT is sum of static plus dynamic pressure. Dynamic is rho half rho v square. So, and or from this you can calculate the velocity as the root of 2 into total pressure minus static pressure by rho. So that is the expression for a particular point, you can say. So based on this you can have the Pitot tube working explained. So Pitot tube basically has it's a tube which has two sets of openings, you can say. One set is the front opening, and then there is a side opening around this edges. So when the air flows in through this, the aircraft, this is modeled like this. So when it faces the air, what happens? It is the air becomes standstill at this point. This point the air becomes a standstill. So this is a static pressure. So, and this are connected to sensors, transducers internally. This particular chamber is connected internally to pressure transducers. Any type of pressure transducer could be there. You could have a piezo electric transducer maybe, so that the pressure is converted to an equivalent electrical signal. So that is measured there, and then so this is the total pressure that is measured. So that is the total pressure that is measured at this point. So that is the front point is the total pressure. So whatever pressure is measured at this point is the total pressure, and again the air which flows through this edges, that is going to be measured as a static pressure. So this green openings, these are on the side, the set of openings are there, that is internally connected to the static pressure. Okay, so that is the flow is not slowed down at this point, so it is static. So these are otherwise called as a static rings. This are called as a static rings. So we have both the parameters PT and PS. So now it is a matter of plugging in the rho value and just finding out the velocity. So that is calculating the velocity. So that is the Pitot tube. So Pitot tube is a very reliable device. In fact, it is all the first three devices which you learn in this module, that is orifice plate, Venturi meter, and Venturi tubes and nozzles, and also Pitot tubes. They are all applications of Bernoulli's principle. Now moving on to the next topic, that is a positive displacement type of flow meters. If you recollect, we mentioned that so this completes orifice plates, Pitot tubes, and Venturi tubes. We are not discussing these as of now. We will discuss Coriolis meters later, mass flow meters later. These are mass flow meters. This Coriolis meters, these are mass flow meters. We will discuss positive displacement type of meters and then come back to this. It will be the way we will go about this. So so positive displacement type of flow meters, basically this is something which you commonly encounter. What type of meter is this? This is a water meter, which is domestic water meter. Here you will have a small chamber within which the fluid circulates, and it will be moving some mechanical structure within that thing. And hello, yes, someone raised a hand. No. Okay, fine. Okay, I thought there was a doubt, that is what, or it was there was a disconnection or something like that. Anyway, this basically there will be a very precise chamber within this meter through which the fluid flows, and in this during the flow it will be causing movement of a particular structure. So as I mentioned earlier, in this domestic water meters, mostly you will have a disc which will be nutating. Nutation is just like your top, നിങ്ങളുടെ പമ്പരം ഉണ്ടല്ലോ, പമ്പരം, the top, when you just put it on the ground and it is rotating, when you give and while it is rotating, if you just slightly touch it with your finger, it is going to waver around this point. That is nutation. And this nutating disk type of flow meters we'll see. So basically you could use variety of things, Hall effect sensors or anything, to convert this mechanical type of flow meters to an electronic type of flow meters. That means you can put magnets on the rotating mechanical component, and then that is going to be a Hall effect type of thing, Hall effect sensor. Or so variety of options are there to get an electronic output from a mechanical positive displacement type of flow meters. Okay, so the first one is a nutating disk flow meter. If you see the diagram, that will be much clearer. This diagram, this is much clearer. So this is your disk which is mounted on a sphere. So this is a sphere, and you have mounted the disk on this sphere, and through the axis you will have a spindle. Means through the axis of this sphere you will have a spindle or a rod, you can say, and that rod is connected, not connected, it is going to be touching. This is that rod, the spindle which is rotating about. This GIF is from a particular website. Okay, and this is going to turn this top dial, the counter will be rotated by this. There will be a stick which is, so when it moves around, it is going to rotate this counter. So the fluid flows in through this structure, it comes into this chamber and through this point, and it will just exit out. So when this comes in and exits out, it is going to rotate this disk in a particular manner. It is nutating. This is not a rotation, rather it is nutation. That is why we call it a nutating disk. And you need to draw the structure. Okay, for explaining these things, you will have to draw at least this particular structure. So a disk on a sphere, and it is rotating. So this is the basic principle of a nutating disk flow meter. So this chamber, so we are causing this disk, you are correlating this disk movement to the fluid flow. A particular amount of fluid is there in this. We very specifically know how much it is, and it is precisely machined. Okay, and it is going to create a rotation, and you are correlating this rotation to, say, you say liters, kiloliters per hour or gallons per hour. You will calibrate it. Calibrate is easy. Okay, so these are really simple things, and it is accurate, and there is no drop in the pressure. Only problem is that particles may get suspended. You will have to put a mesh. All problems associated with domestic water meters. We have usually problem here. Okay, we have been changing the meter for every 3 or 4 months. Water gets what do you say? It's in a low position. No, it's at a low position. So rainwater gets into the meter. It gets damaged. That's what. So then another type of flow meter is a sliding vane type of flow meter. Sliding vane type of flow meter, it is a bit more tricky to visualize. I'll just say what is it. Say you will have a drum which is rotating, and this is your fluid flow. Okay, this is your fluid flow. Okay, this is the fluid flow, and this drum is going to rotate based on this when the fluid flows in, and the on top of this drum you have connected some vanes. Vane means, you can say, rod like structures, usually of plastic or something like that. They will also be rotating alongside. Okay, and they'll be also rotating, and at the shaft, this portion looking into our face, you will be have connected the counter, and this counter will be rotated because of this rotation of this particular vane. So you would have seen some structures, maybe you wouldn't have identified it, but a rotating vane, or it's otherwise called a sliding vane or rotating vane, both names are interchangeably used. So sliding vane type of flow meter or rotating vane type of flow meter. Then another type of flow meter is a lobed impeller. Lobed impeller, also you have a chamber within which you have impellers. Impellers, these are structures made up of lightweight materials and maybe plastic or something, and it will be rotating at two angles. Say this is the rotation, this is the rotation. So when the fluid flow comes in, this is going to rotate this particular thing in the clockwise, and the other one is in the anti-clockwise direction. So this is the lobe impeller. So and you are pushing out the fluid. Okay, you are pushing out of the so this is clockwise, this is anti-clockwise. If you trace the path, so the fluid is just pushed out. That's it. Clockwise, anti-clockwise. Okay, so this is a lobed impeller type of flow meter, and you are going to connect it to counter. The shaft is connected to any of these impellers. You can just rotate a counter like this, counter like the one which you see on a counter like the one which you see on a domestic water meter, that could be rotated. If you have a spare water meter, old one, in your home, I suggest you just break open. I have 3 of them here. Maybe I'll bring one of them to the class when I come. Okay, I will break it open and see what is it. Then the other one is a reciprocating type of or a piston flow, reciprocating piston flow meter. Say you will have 2 piston like structures which move alternatively. Okay, and say the water enters here, and we will just slide it up, and it will as a result this pushes down, and then the circulation is over. Then this is going to let out the water through this path. So this is going to circulate in alternate way. So these are all the key idea in positive displacement type of meters is that you are having a chamber which is of a precise dimension, and you know what quantity of fluid is going to get into this chamber, and it's like a simplest example you can say is that you want to measure the flow rate through the pipe. Say I'll have a empty glass with me. I have 3 empty glasses with me. Say I'll turn on the pipe, I'll keep it at a particular rate, I'll put the first glass under it, when it fills up I'll put the next glass. Then if you take the time required to fill up these 2 glasses, you can get the flow rate. The same idea is there. Same idea is used in positive displacement type of flow meters. That is, glass fill in the time, അടുത്ത glass fill in the time, you can say the flow rate. Okay, you can just find the flow rate. Same principle is used in this PD type of meters. So then next day we will take up mass flow meters. So we'll discuss this mass flow meters next day.